You're watching a Channel 98 NBISD TV production.
Oh, hey there. Has it already been a whole week? Oh man, time flies when you're doing math. Ain't that the truth? Welcome back to another episode of Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, and I've been diligently working at the board here for about a whole week, I guess. I didn't realize that. But hopefully you've been doing other things, and now you're back to watch the second episode. This is the first episode, though, that we're actually going to be doing real live mathematics. If you watched last week, then you know that we talked all about the history of algebra in its 4,000-year-old history, how it's evolved from the ancient Egyptians to what we're doing today. And we're going to cover that throughout the year. So as you're watching, I strongly encourage you to download the worksheets. I've worked hard to prepare worksheets for you so that you can play along right at home. Just log on to the district website at www.newbraunfels.txed.net. Download as many as you want. Work them as many times as you want. And as you're working them, if you happen to have a question, shoot me an email. You can find my email on the district websites, or if you want it, it's kcorpy@newbraunfels.txed.net, and I'll be happy to reply. Let's jump right into today's algebra lesson. All right, so lesson 2. Today we're going to talk about notations, what a function is, and how domain and range relate to a function. Now, as you saw on the first show, hopefully you saw on the first show, algebra grew out of arithmetic, which is really just operations on number sets. So it is important early on to understand the different types of number sets and actually how to represent them. So here are some examples. The first set of numbers are the natural numbers, and these are the first ones to come out of the scene. It came out of people's desire to keep track of their material objects, how many things they had. It's the natural numbers, and it's sometimes called the counting numbers. Now we denote these special number sets with very special letters. So the set of natural numbers, we're going to use this letter N, which is kind of got a double bar right here. And we said that that set then is equal to, and we use this fancy notation, which is what we call a brace. So we are going to use a brace to denote a set. So we say that the natural numbers equals the set of all numbers that are of this variety. 1, 2, 3, 4, comma, and I think you'll see the pattern. So what we're doing is we're going to make a list. 1, 2, 3, 4. This is an infinite set. It goes on forever. But once we establish the pattern, usually with about 4 numbers, we can put these ellipsis points, which implies that the pattern continues on indefinitely. So that's the set of natural numbers. Well, the next set of numbers is the set of whole numbers. Well, basically, this is the set of natural numbers, including one special number that the Hindus were the first to use, remember, the number 0. And we use a double bar W to represent the whole numbers. So we say the set W equals, we add 0 into the mix, 0, 1, 2, 3, and again, if we list about 4 of them, y'all can see the pattern. We put the ellipsis points, and we close it up with the brace on the end. Now notice that every natural number is also a whole number, but not every whole number is a natural number because we got 0. So what we say then is that the natural numbers are a subset of the whole numbers, and we can use subset notation kind of like a less than sign. It's like a fallen over U. We say n, sideways U, or is a subset of the set of whole numbers. Everything that's a natural number is contained inside the whole numbers. All right, let's move on to integers. Well, we got 0 involved. Now we're going to have to start looking at debt. Remember, the Hindus were the first to use negative numbers to consider debt. So if we include all the whole numbers and now the negative natural numbers as their counterparts, we get the set of integers. And we use this double-barred Z to denote that. It comes from the German word zählen, the verb to count. So Z is not a real obvious choice for integers, but you can think of them as the zintegers. That always helps me remember it. So it's the set of all numbers that are the negative integers. So we actually have to start with our dot, 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 comma, negative 3, negative 2, negative 1, counting up to 0, then 1, 2, then 3, and then ellipsis points. It goes on indefinitely in both directions. So those are the integers. These are essentially our marks on the real number line, and then we look at the numbers in between them. Now this is an infinite set as well, and it goes on to infinity in both directions. Just a reordering of this set, though, mathematicians would prefer to order it this way, and I'll tell you why in just a second. If we instead start with 0, and now we list the positive and negative pairs, -1, 1, negative 2, 2, dot, dot, dot. I think you'll see the pattern. The benefit of this one going to infinity only in one direction basically means that mathematicians can actually count this infinite set, whereas the top set, they can't count it. So although they're really both the same set and there's an infinite number of variables, the crazy thing about math is we say the bottom set is countable and the top one is not. Ooh, that's kind of crazy. Okay, let's look at rational numbers. Rational numbers are going to be a step up from integers. So we actually are going to list rational numbers a little bit differently. We have been listing numbers so far. You cannot list the rational numbers, though, in any proper sequence, because as soon as you start listing them, you're going to skip over some. So instead, we say it's of the form P over Q, such that P and Q, oops, I messed that up. How about this? P comma Q are elements of, and we use this right here. This is the Greek letter epsilon, and we use that letter to say is an element of, or are members of the set of integers. And so we can put our little z there. And we don't want to divide by 0. That's one of the cardinal rules of mathematics. So we'll go ahead and make a note here that q shall not, will not equal 0. And then we'll close our set. Now that's a language right there. Some of the reasons people have difficulty with math is because they have to learn the language. So let's read this together. Rational numbers are the set of all p over q, numbers of that form, such that p and q are integers. So if you take any two of the numbers of this set, except when q is 0, and you take one divided by the other, you're going to get a rational number. We actually use the letter Q with a double bar to denote that because Q stands for quotient. And this is actually a ratio or a quotient. Now, these are numbers like examples. We get 2/3. We can get negative 3/5. But some of our decimals are also rational numbers, like negative 2.5. That's a decimal, but it's a terminating decimal. It's the same as negative 5/2. Numbers also like 1.3 that terminate like that are also rational numbers. We can write that as 4/3. So rational numbers do also include terminating decimals or repeating decimals. Now we move up to irrational numbers. And irrational numbers are a disjoint or mutually exclusive set of numbers from the rationals, meaning that they don't overlap at all. And there's no nice way to list the irrationals. They come in all different shapes and sizes, and they look very different. So what we're going to do is we're just going to list some examples. The most famous example arguably is pi, which is approximately 3.14159. And it goes on forever. There's actually computers right now that are still calculating the decimals of pi. And you could buy books about this thick where every page is just decimal digits of pi. They never repeat in a regular pattern, which makes it irrational. This cannot be expressed definitively as the quotient of two integers. Another famous one is the square root of 2. There's a story about how the Pythagoreans actually killed a person for knowing about the square root of 2. And that's a long story. We don't have time today, but you can look it up on the internet. It's irrational. And then we got another number, e, which is about 2.718. And that's Euler's number. It's the natural base. And it's another famous irrational number that we'll be encountering this year. There is no letter to denote irrationals. We just give examples here. Now we look at the real numbers, and we're going to primarily concern ourselves this year with real numbers. Real numbers are basically the set of all numbers, and we use this double barred R. It's the set of rationals and the set of irrationals. And that's it. So we take those two sets of numbers, which do not overlap, and we put them together, and we got the real numbers. And there is one other set of numbers called the complex numbers, which is the imaginary numbers. But we're going to save those until we get to the fundamental theorem of algebra later on in the year. Okay, let's move along. Now you notice that as I was doing that, I was using the notation with the braces. What I was using is roster or set builder notation. There's another one we're going to talk about now, which is interval notation. So let's talk about rosters specifically now. A roster is just like a sports roster. It is a list of elements or members of a set. You can actually list them. They can be finite sets or they can be infinite sets. If they are infinite sets, though, they have to be listed in a sequential order so that the pattern is maintained. For example, the set of whole numbers less than or equal to 5. Well, we can start listing that. We usually give our sets a name, so I'm going to call this one the set S. And what's the first whole number less than or equal to 5? Well, remember, 0 is the first whole number, so I can list it. 1 is less than or equal to 5. 2 is less than or equal to 5. 3 is less than or equal to 5. 4 is less than or equal to 5, and believe it or not, 5 is also less than or equal to 5. So that would be our set. And this is a finite set. It has 1, 2, 3, 4, 5, 6 elements. So we can say that the cardinality of the set equals 1, 2, 3, 4, 5, 6 numbers. So the cardinality is the number of elements in the set. So this is a finite set. The order in this case, because it is finite, doesn't really matter. We can rearrange these elements inside the set, and we have the same set. Let's look at this next one. The letters A of the alphabet. So we're going to call our set A, and it's going to be the set of all, let's see, A, B, C, y'all see the pattern, D, E, F, G, blah, 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 right, X, Y, Z. So this is where I've continued the pattern in between here, but it doesn't go on indefinitely. So when I come back here to X, Y, Z, this is another way to list a set. It's a finite set, but it's very long. Now we have to assume that people know how to generate the pattern. What's the cardinality of this set? Well, the cardinality of this set is 26. We get 26 letters in the alphabet. So that's the size of the set. Let's look at the next one, the set of natural numbers. Well, we've already looked at that. We call it double bar n. And remember, it was 1, 2, 3, 4. And this one is an infinite set. So unlike up here, I'm not going to come down. What's the largest natural number? Well, it goes on forever to infinity. So this is an infinite set. Okay, but it still is a roster. We're listing them. The set builder set is the next one, and it's similar to roster, but instead we have to define the properties of the set. And it's like what we did with the rational numbers, remember. We can't actually list them, so we define a set of properties that make the set unique, what it is. So the rational numbers, remember, are the set Q, such that they are this form, P over Q, such that P and Q are elements of the set of integers, and of course Q cannot equal 0. So notice this is not a list. We read this vertical bar right here as the word such that, and what that does is it says they have to look like this, but then we're telling what these numbers themselves have to be. And now we can generate the list from this rule right here. This says take any two integers except when Q is 0 and find the ratio, and you have a rational number. Now you could take any integer like the number 5 and you could turn it into a rational number by putting it over 1. So really the integers are a subset, remember, of the rational numbers. All right, let's try this using set builder notation. The set F of integers greater than or equal to 15. Greater than or equal to 15, and they have to be integers. So how are we going to do that? Well, let's start with our capital F, and we're going to use set builder notation. So if we're calling this big F, typically we want to use this lowercase variable. So it's going to be the set of all F such that F is greater than or equal to 15. But we're not done there, because if we just closed it up, we would assume by default, if we don't say what type of numbers F is, that we're talking about the real numbers, which means this could be 15.1 or 15.2 or 15.3. But we want them to be integers. So we'll go ahead and put a comma and say, oh yeah, by the way, F is an element of, there's that epsilon, the set of integers, because that's what it says. Now we really wouldn't lose anything in this case if we had put the set of natural numbers here or the set of whole numbers here, because once we're out past 15, the natural numbers and the whole numbers and the integers are pretty much the same. Okay? But it doesn't hurt to go ahead and put the integers since that's what they specify. And the last one, let's try this. The set of all positive even numbers, we're going to call that the set P. Positive even numbers. Well, can we list that in roster notation? Yeah, let's try that first. Positive even numbers. So that would be 2, 4, 6, 8. Y'all see the pattern? Dot, dot, dot. And we close it up. But let's try to do it with a set builder notation. It would be the set of all numbers, little p, such that little p equals 2 times n. Where? What type of number is n? N is going to be a natural number, a counting number. So what's the first counting number? 1. So if I plug it in to generate it, 2 times 1 is 2. There it is. The next counting number is 2. 2 times 2 is 4. The next counting number is 3. 3 times 2 is 6. So this would be a way to write it in set builder notation. Another way to do it is using interval notation. And interval notation is primarily used for real numbers. That's the real difference. We have to be talking about real numbers. And what it does is it lists a set of all the numbers between two endpoints. we have to use parentheses when the endpoint is not included, and we have to use these brackets right here if it is included. And what you have to do is list the endpoints and intervals in increasing order. And I will show you what I mean right now. Now let's go ahead and make this note. I've already mentioned it. If the set of numbers in a set is not specified, then we have to assume that we're talking about the set of real numbers, which is the set of irrationals and rationals combined. All right, let's take a look at this one. And we'll use interval notation. The set of all numbers between 3 and 5 inclusive. Well, when I say the word inclusive, that means that I want to actually get 5 involved. I want to go to 5, but I don't want to include 3. So how am I going to write that as an interval? Between 3 and 5, it's going to be 3, comma 5. We can start like that. We're starting at 3, comma, and we're proceeding to 5. But because we don't want to include 3, I would have to put a parenthesis there. And because it says I do want to include 5, I am going to put a bracket. And that would be interval notation. Now, let's go ahead and write this using set builder notation, because we can also do it in set builder notation. We'll say the set of all numbers is going to be the set, I'll use n, the set of all n, such that n is between. So we can actually physically write n between 3 and 5, and we'll close the set. So if it has to be between 3 and 5, n has to be greater than 3, and it has to be less than or equal to 5. So these two notations are actually equivalent. Set builder, a little more formal, and interval notation a little bit more quickly. But interval notation only works for real numbers. Let's try this one. The set of all numbers greater than 0. Well, in interval notation, we will start at 0, and it says strictly greater than, so we're going to put a parenthesis, not a bracket. And then we need some placeholder for a right endpoint. How far greater than 0 can we go? As far as we want. So we get to use this cool infinity symbol right there. It's a fallen over 8. And infinity, since it's not a number, we can never include it. So infinity in interval notation must always get the parenthesis. Now in set builder notation, this would be the set of all numbers n such that n is greater than 0. We don't have to say less than infinity in set builder notation. If we just say greater than 0, we're implying that it is. All right. Let's try to do this one here. The set of all numbers less than or equal to 2 or greater than 3. Well, you can't be in both of those intervals at the same time, less than 2 and greater than 3. So this is a disjoint or interval. So let's start with the first one. Less than or equal to 2. How far to the left of 2 can we go? Well, we get to start as far left as we can think of, which is negative infinity. And this gets a parenthesis. And we'll proceed all the way up to 2, so comma 2. Do we want to include 2? It says less than or equal to. So that gets a bracket, sorry. Now the word or in mathematics, we use this fancy U for sets and intervals, and this is the union symbol, and it's just a fancy mathematical symbol for the word or. Well, now we want it to be or greater than 3, strictly greater than 3. So we're going to pick up at 3 with a parenthesis. We're not going to include it. And we will go as far to the right of 3 as we can, which is positive infinity. So that would be the interval notation for that set right there. Okay. Before we go to break, let's look at this one little quote. I heard this awesome geography teacher at New Braunfels High School. He was walking down the hall, and I heard him say this, so I thought I'd quote him. Mr. Wenzel was heard in the hall saying, "Algebra is awesome." There you go. It's time for a quick break on Deja Vu. It's Algebra 2. But while we're gone, ponder this question. What did 0 say to 8? The answer when you get back.
I smoked weed and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot at dying out there in the real world. Driving hard to the rim, ice skating with a girl. Now you want to keep yourself alive, you go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. And when you're gone, I hope you're thinking about the answer to the question, what did the number 0 say to the number 8? The answer is, of course, nice belt. Yeah. Let's get back to the algebra. All right, so that's the notational part. Now we want to look at functions. Throughout the year, we are going to be studying functions and solving equations. involving functions, and it's going to be very important to understand what in the heck functions are and why are they so important. Why are we studying them? Here's an example that might get you to appreciate the value of a function. Imagine that you go into the store to buy a bag of chips, and you get to the checkout, and the clerk rings up your chips, and the clerk tells you that your cost is going to be either $2 or $5. $2 or $5 for the same bag of chips. What? I mean, that doesn't make any sense. Okay? That is where functions come in. A function is a relation between two variables, like what we choose to buy and what the ultimate price is going to be. That's essentially our independent choice of what to buy, our independent input, and the ultimate dependent price or the dependent output. Now, the important part of the function is that for every independent input, we bought one bag of chips, that was our independent input, there is no more than one output. So you can't have two costs at the register for the same chips. Pick whatever you want, but when you get up to the register, there's one price. Okay? As many inputs as you want, but only one output per input. That's how we make sense of the world, and that's what functions do, and that's why we study them. So in our case, since we're going to be looking at equations this year, we're going to call our set of independent inputs the domain. And that is a set of numbers, so we're going to have to use set notation. We usually use the variable x or the variable t to denote our independent variable. Now the set of all dependent outputs, like the costs, it depends on what we input, we call those the range. And that's because we get a variety or a range of outputs depending on what we independently choose to put in. Now the range is essentially our function values, or they'll be the y values on the graph. And we denote it as this right here, f parentheses x close parentheses, and we read that as f of x. Okay, let's talk about it a little bit. F itself is the name of the function. We can have other functions like r of x or p of x. So f is the name, and x is the independent variable. But f of x itself, the entire f of x, are going to be the outputs, or again, the y values on the graph. Got it? Now here's an analogy that may or may not help. Think of a function as a machine that takes an input, usually in algebra a number or an algebraic expression, and it transforms it into another number or an expression. For example, look at this little function right here. F of x is x plus 7. We can say that we could drop in any input x right here, which means we drop it in there, and it'll add 7 to it, and it gives us an output. So we can call this our add 7 machine. Okay? That's a pretty cool machine. Here's a little diagram of the machine. Drop in an x, chugga, 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 add 7, spits out whatever the input was plus 7. Pretty neat little machine. Now, evaluating functions is going to be very important. The important thing about the function notation is that you see the independent variable here, and it's preserved. So you could think of this as being kind of like a template. F of parentheses equals parentheses plus 7. Whatever you put in here for x, you're going to put all the way through the equation for x. So for instance, if I put in a 2, f of 2 is 2 plus 7, or 9. So this machine, you drop in a 2, get out a 9. That's a pretty sweet deal. Here's another one. Drop in a negative 2. Well, it's negative 2 plus 7. Drop in a negative 2, get out a 5. But we can drop in letters as well. Drop in an m, and you get m plus 7. We can't simplify that anymore, but we do get an m plus 7. We can also plug in entire expressions like 2x minus 1. If a 2x minus 1 is here, f of 2x minus 1, then we drop it in here for x, 2x minus 1 plus 7, and we can simplify that. 7 minus 1 is 6. So we get 2x minus 6. Okay, now we're going to be interested throughout the year in which sets of numbers can we plug into our function machine that are going to actually yield or give us an output. Not every single input will always work. So we want to identify the values, the inputs, that are allowed to go into the machine. In other words, we want to find the ones that will not yield an output because it might break our machine, and we don't want that, do we? Now, the two operations that we really need to be on the lookout for that are going to break our function machine are division by 0 and taking the square roots, or in that fact, the eventh root, 4th root, 6th root of a negative number. So we need to be on the lookout. Now, for our machine above, all values of x will work. There's not a single real number in the whole world that you can't add 7 to and get a number. So we're going to say that our domain we use big D, and since our function was named f, it's appropriate to put a little subscript. We call that D sub f is the set of all x's such that x is an element of the real numbers. That's how we do it in set builder notation, or we can write it in interval notation from negative infinity to infinity. That's a cool one right there. Now the range, I'm not going to do much of the range today. The range in this case is in fact all real numbers as well, but sometimes it's very difficult to determine what the outputs are. But what they essentially are all the different values that our machine will spit out from all the inputs that we're allowed to plug in. We'll talk about that on another show. All right, let's close the show up with a little bit of segment I hope catches on very quickly called Deja Review. There it is. Okay, let's look at two functions that actually have restricted domains where we are not allowed to plug something in lest we break our machine. The first one is g of x equals 1 over x. Now notice that the name of the function is g, not f. That's okay. Our independent variable is still the familiar x. What this function will do, input an x, and it'll spit out, whoop, 1 over x, the reciprocal. So we can call this the reciprocal function, or familiarly, the flipping machine. Okay? Now, notice also that we can't divide by 0. So anytime we have a denominator, and especially a denominator with a variable, certain values of that variable may make the denominator 0. This is a real easy example. So ask yourself, what value of x, when I plug in for x, will give me a 0 down there? Well, it's real easy to see that x shall not equal 0. When you plug in a 0, you have 1 divided by 0, and that operation doesn't work. Any other value of x is going to be okay. So we have a singular value that does not work. Now, all the rest of them do. So sometimes, if there's just a handful of values that will not yield an output, that aren't in the domain, it's easier to list the domain as the ones that don't work, and then we'll assume that all the others do work. So if we want to list this in set builder notation, we'll say the domain subscript g, the domain of g, and then we put a colon. And now we're going to use the set builder notation. It's the set of all x such that x does not equal 0. And all the rest of them work. Okay, now if you want to do this in interval notation, you're going to have to list the ones that do work. So here's the equivalent domain in interval notation. We have to start at negative infinity, and remember it gets the parenthesis, and we'll cruise all the way up to 0. Union 0 to infinity. So what that does is it goes right up to 0 and then steps right over it and keeps on going. But we do not include 0 because there's no brackets there. Pretty cool. All right, so division by 0 affects the domain. Here's the last one. Example 2. This is called the radical, or the radical dude function, as I like to call them. It's r of t. So the name of the function is r. Our independent variable is t. Now, we don't have a denominator here, but we do have a radical, and we cannot have negatives under the radical. So any value that gives us a negative under the radical will not be in the domain. What are some of the values of t that when I plug in give me negative? Well, negative 5, negative 4, negative 22.3, negative 5 billion. There are many, unlike the last example where there was just the 1, 0 that didn't work. And so in this case, if we have a radical, we want to try and figure out which ones work, because there's just as many that work that don't, infinitely many. So what we'll do is we'll take the number under the radical, which is called the radicand, and we'll say, okay, that thing right there, it needs to be positive. It has to be greater than 0. Square root of 4, square root of 2, they all work. And it can be 0, so it has to be greater than or equal to 0. The square root of 0 is 0. And then we solve this inequality. Well, this one's already solved. So really, that's the domain. So as long as you're plugging in a value of t that is either greater than 0, positive, or 0 at the very least, it'll work. Any negative number less than 0 will not. So let's state the domain. The domain sub r is the set of all t's now such that t is greater than or equal to 0. Or if we're writing an interval notation, the domain of r is bracket 0, comma, infinity. There you go. Radical, dude. All right, so some real basic information covered on today's show. Didn't get too heavy into the algebra, but it's really important that you understand the notations that we talked about today, because it's no use in finding the right answer if you can't present it in the proper manner. And that's what the set notation, the roster notation, and the interval notation are all about. Finding domain and range is one of those important things that is never going to go away, and we will be looking at domain and range pretty much all throughout the year. So I think it was a pretty good first show. I hope you enjoy the show, and I hope you enjoy me next week for episode 3. where we do some more math. Until then, though, I'm Kevin Corpy reminding you to do your homework.